All right, so this is, I guess, part 4 or part 5. I'm a little, um, I'll have to check that. I've been working on other things and I've been away for a bit, but now I have some time to continue this particular series. So, in the previous couple of streams, we've covered, uh, the basics of the transformer architecture. We looked at things like input embeddings, positional encodings, and then we talked about other blocks, things like the normalization layer and the feed forward layer, etc., which are all important. Uh, so basically, just to sort of pictographically explain this, so we talked about input embeddings, basically taking your input, which is in this case just English language, and then sort of representing the English words, each word in this case, because when we do the tokenization, we're not necessarily doing sub-word level tokenization, but we're doing, for simplicity's sake, since we're building a very simple implementation of the transform architecture, a full word tokens. And then you add the positional information over there using the positional encoding piece, which is this part. It's a simple add operation. And then whatever we get, we sort of pass to this block, which we have not yet covered. And the goal is to actually go ahead and cover this block. Needless to say, this is the most important block in the transformer architecture, both in the encoder and the decoder. You'll find this exists. The other blocks that we've also sort of looked at was the normalization layer, where we're simply just, normalizing the any input that we get so that it's within you know, a range that's amenable to computing. You don't want really large numbers or really small stuff. You want it within a certain range of sorts. And then there's the feed forward layer. We talked about that as well. Today, our focus is going to be the multi-head attention block. And again, as I've stated, all of this is something that you can pretty much pick up from any tutorial. What we are focusing on is the Rust implementation of the transformer from scratch. How does it actually look like? And how does the implementation work? So we'll look at that part. So before I get into this, let's actually talk a little bit about what this multi-head attention is. If you were to simply look at it, it's just this formula, which is Q times K transpose divided by the square root of dk times V. And you're wondering what the hell is all of this? Well, you remember this particular multi-head attention block actually has three sort of inputs. Well, those three inputs are nothing but Q, K, and V. So whatever we get from computing, adding the input embeddings and the positional encoding, which you've seen in the previous streams, whatever encoder input you've been able to create, you make three different copies of that. In our case, that's actually, according to the paper, it's 6 by 512, but in our case, that's actually 8 by 512 because we're going for, 8 words in, you know, in one batch. And then each word is a 512 dimension vector. So we basically take the 8 by 512 matrix, and then we make three copies of it. So QKV are those three copies. And then what we do is we simply go ahead and multiply. This is a matrix multiplication of Q with the transpose of K. When you do something like that, what happens is you are actually creating a new matrix that's a 6 by 6 matrix in this paper, or in our case, that's an 8 by 8 matrix. But the idea is you are trying to relate the words in your sentence with other words in the same sentence. You're trying to come up with, the degree of uh, some sort of a relationship, you know, and uh, effectively in a very simple way, you can say that you're trying to say, okay, which words go well with which words over here. If you see this word, then you can probably expect this word after it, sort of a scenario. So ideally, if you see here, the words, the scores that are diagonal, this entire thing, are usually the highest because this word with this word sort of seems the same thing. So probably have a, you know, uh, the score is probably the highest. Now, all these values are just random, as the slide says, but this is just an example. So what we need to do in our case is we need to implement this. And then we also need to apply this thing called the softmax, which is just a function that takes uh, your input and applies uh, the softmax to it. We'll talk about what the softmax is. So, and the thing is, why is it called? So this is basically self-attention. This is what we want to do. Uh, but then what is multi-head? Let's talk about multi-head as well. Uh, so multi-head is basically us trying to talk about the fact that we can't do this computation, which is this times this divided by 512, and then again that times v gives you the actual attention score. If you want to do this all in once, you can do that. That's okay. But you actually want to split it up. You want to split up the matrix, that's the QKV, into smaller matrices, and then do your calculation so that you can take advantage of the ability to parallelize your compute, basically. And in that case, that's exactly where multi-head attention comes into the picture, where what we are effectively doing is we are going ahead and taking the input, which is QKV. We sort of again multiply that by another matrix, uh, which is D model by D model. You get something called Q prime, K prime, and V prime. That is what you sort of split up into smaller matrices. Each one is a head. So if you divide Q prime into four, that's four heads, then K and V. Then you do the same, you do the same calculation, and that is what becomes the actual result. So each head is calculated individually, and then you concatenate them, and then finally you complete the formula by computing V. So that is pretty much uh, you know the essence of uh, self-attention and its implementation as well. You actually implement this in this manner. And then there's, if you start looking at it, you will start seeing that, when you start analyzing these scores, you will see something like this. For example, making is a word, and there's degrees of affinity, you can say, to many different words. All right. Uh, 2009 making has like a high degree score. Making laws, making 2009, making more, all of the stuff has varied uh, levels of affinity with the word making. You will sort of be able to tell when you look at these scores. That's kind of what the paper actually, it's a simple idea, as I said. That's about what we're doing. All right, so without getting into too much detail about the actual paper itself, let's look at the implementation specifics. In the implementation, what are we saying? We'll basically start out by saying multi-head attention is our block, as we've done in the previous streams. And then Candle has the Candle framework. I am still debating this. I'm not too sure whether Candle's going to stick with it, but Candle's actually subdivided into individual other crates. For example, Candle core has the core operations and the core types, the core primitives. Candle NN has the NN related you can say types and traits, etc. Uh, Softmax, for example, is an operation, and that's included in Candle NN. So we import both of them, and we basically build out our multi-head attention block. The way we do that is, if you go look at this diagram again, you'll see that this WQ, WK, and WV are, the new matrices that you need. You can assume this is part of your state that you're going to need. Uh, so I'm basically going to include them here. And I also need WO, which is this part. So I've got that as well. So I've got those four. Then I also need to know what is the dimensionality of the word or the tokens that we're dealing with. We include that. We talk about, because we're talking about multi-head attention, we want to talk about, how many heads are we splitting the actual matrix into, and the size of the head after the split for each of the heads. And then there's also dropout. So the first thing is I just basically create an instance of my multi-head attention block, and then I simply go ahead and do what we normally do, which is forward. One of the interesting things that you see is, let's actually look at the implementation. But before I show you the implementation, let me let me walk you through this so that I can show you the results, because we actually do have some tests that I've put together to show you what happens when you actually run through this, so that you can actually see it pictorially or pictographically, whatever that is. So once you have your multi-head attention block, according to the paper, what do you need to do? You first need to go ahead and uh, do Q times K, right? Uh, so actually, yeah, you need to do Q times K transpose divided by 512. That's kind of what you need to do first. So let me actually go ahead and calculate Q prime first, because if you look at this is what you need to do. You're not going to directly take Q and then split it up. You're going to actually take Q prime and split it up. So let me go ahead and do that. That should be straightforward. So this is basically batch sequence length by D model, which is one batch. Sequence length in this case is 8 in my case. And then the D model is 512, because each token is about 512, has about 512 dimensions. This operation will again yield a tensor of the same size. And then comes the interesting part. Now I have the Q prime. Now I need to go ahead and do what is, basically split this up. So this is the interesting part. You have reshape pretty much everywhere, including in PyTorch as well. In Candle, the interesting thing is, in PyTorch, you have like two APIs. You've got the reshape and you've got a view. View is usually, you don't do any copying, and underneath when you actually do view. But in reshape, you could end up doing, creating copies of the tensor, because you're literally going ahead and reshaping the tensor. So you may need to end up copying. In Rust, you only have reshape, or rather in Candle, you only have reshape. Again, it's generic over the tensor that you want to operate on top of. The idea is, it basically simply means this. If the tensor that you've supplied to the reshape operation is contiguous, that means all of its elements are laid out one after the other in memory, and that's in row major style, you can simply go ahead and reshape it. That reshape is going to be like a view. Otherwise, it's it's actually going to do the copy, as the documentation for the API suggests. Reshape returns a tensor with the target shape. The number of elements is the same. If the input tensor is contiguous, this is just a view. Otherwise, you create a new storage and copy the data over, and the return tensor is always contiguous. That's self-explanatory, I think. So when you apply this operation, I want to go from sequence length D model to sequence length, number of heads, and head size. I basically want to reshape the tensor that I have into this particular shape. And then I want to transpose two separate dimensions. We got to print this and see what that looks like. We'll do the same thing for key and value. If you just look at this diagram, it's kind of what you want to do. I create these, this, and this, right? Once those are done, then you would want to calculate the attention scores. And the attention scores over here are pretty straightforward. The attention score is nothing but you want to calculate this, right? So Q1 times K1 transpose divided by DK, and then you get the head. That head, you hold on to it. You need to sort of concatenate all of that and then multiply that. All right. So That is basically what's happening in the attention score calculation. We are doing a little bit of checking uh, because if you see, uh, you want your D model to be divisible by the number of heads because you want clear, you know, you want equal sized smaller matrices. So that's something that you need to do. Uh, but yeah, effectively, we check all of those things. If it's out of range, etc., we check all of those things. But the attention score is effectively going to do the same thing. You are going to take the attention score. Uh, in this case, this has to be contiguous. So I'm just ensuring that this is another thing. You can actually take an existing tensor and create a contiguous version of it, if it's not already contiguous, right? Um, you can do that. So you don't have to like worry about whether my tensors are contiguous or do I have to do something else. That's something interesting that's already provided. The other thing that you need to notice, all of these are packaged up in results, in the result type. So if you see this is a result. If you see the broadcast, that's a result. If you see the matmul, that's a result. Everything's a result. Okay, so you'll end up having a lot of question marks just to do the safe, unwrapping of your uh, operations. Uh, I kind of like it for now, but I don't know if you have way too much of this because there's actually a lot of this when you keep writing your code. Uh, how does this really translate when we are actually doing the debugging part of it? We'll see. We'll see how that works. But in any case, you do the attention scores are calculated. By the way, there's no fault. If you notice something, you're not calculating it for each thing because the way you do it is you have one tensor, which is actually of this particular shape. One tensor that contains, four of these matrices, and then we go ahead and uh, basically do the same thing over there. We do the matrix multiplication on top of that. So that's good. That works. And then there's another mask concept. We haven't touched this, but basically, let me see if I can just quickly go over this. Uh, so if you see here, mm, yeah, masked multi-head attention. So if you do not want some of these words to interact with basically the word that comes after it, you don't want the word before it to interact with it. That means future words. You don't want the words in the past to interfere with the words in the future. You can pretty much go ahead and mask them out. And the way you mask them out is you basically set them to minus infinity, and then when you apply the softmax, this sort of becomes zero. Okay, that's kind of what we're focusing on. So as it says, all the values above the diagonal over here are replaced with some value close to minus infinity. Obviously, we can't represent real infinity. So we'll have some really large number. And then when you apply the softmax, all of that will go to zero. So you can go ahead and do that masked multi-head attention. All right. All of this is just playing around with tensors to ensure that you get the result that you want. That's how I understood this. Okay. So I get my raw attention scores. Then I want to apply my mask. I get to apply that. I can print that out. Then I apply the softmax. Uh, so the softmax is basically rescaling the element so that the elements on a slice of fixed index and dimensions are between 0 and 1. Uh, this essentially means that you want to do this. So, for example, if I went ahead and did something like this, which is I this is my tensor, so I've got these values, and I applied the softmax, and softmax is applied on dimensions. So this, if you see this particular tensor, this is a 2 by 4 tensor. So I am applying it on the second dimension, which is the column dimension, because I think Candle uses row major style. So when I do apply it, uh, I will be able to sort of round off everything within that 0 to 1. So the entire uh, elements, let's say within this row, should add up to 1, right? So that's the most important thing that you will be able to, make out. That's what the softmax does. So it's sort of a normalization strategy that is what you're trying to end up with. Okay, I hope that makes sense. That is what softmax is. So you apply the softmax, you get that out. And then the final score is you want to basically do this, which is this times WO. So you concatenate all of this, then you get this, then you multiply that with WO. Finally, you get your, attention score. That's what you return. All right. So by the way, this matmul is going to end up getting pushed out to obviously our GPU. That's exactly where you want the GPU to do this. There's a lot of work that needs to be done. So you want the GPU to do this and you want to push it over there. Okay, so now that you've seen this in terms of the APIs and the pieces that need to come into play, you see that, this very much resembles the PyTorch API, except uh, there's a lot more focus on, how you're managing, how much memory you're allocating for things like reshaping, how you handling uh, failure conditions when we talk about the leveraging the result enum to basically uh, be the return type for every operation that you're pretty much doing, be it reshape or transpose or check whether it's contiguous or whatever it is on a tensor. Everything is pretty much a result, and I actually think that's a good thing because there's no room for you know let's figure this out at runtime kind of a thing. Obviously, that's not possible in Rust, but when you actually design something with that thought process in mind, uh, down the line, you actually will see the benefits of that. So cool. One of the things that I did not mention is, things like linear with name and how are we figuring out what the mask is. All of this stuff is actually available in the library or in Candle itself. I've just taken their implementations, not, I don't want to like reinvent it. It's there. Uh, so let's actually start off by looking at, some of whatever we're printing out. First, let me actually do the main test. Let me actually run the full multi-head attention block. That means we will go ahead and do two things. We will get sorry, not this. We will get the input embeddings. We'll get the positional encoding. Uh, we create the um, what is called the encoder input, and then we go ahead and um, supply that to the multi-head attention block, and then let the multi-head attention block do its thing. And then we look at all the intermediate transformations that are happening. I'm just going to print all of them out for us. Okay, so if I want to do that, since I've already done this, let me go ahead and do that. Yeah, this part takes a little bit because the tokenization, when you're looking up the tokens in your token map, you tend to end up spending some time. So the loading data actually does require some thinking. How do you want to do the load? But let's look at this. So vector embeddings are your input embeddings, and positional embeddings are, we've already seen this. So this stuff and this stuff, we've already seen it. You add both of them up, you get your encoder input, which is this. Now, the interesting thing that we want to see, which is this, okay? The interesting thing that we want to see is what is Q prime? You can see that this is Q prime. When you actually take that high dimensional matrix, because I haven't shown you what the, what Q, what this is, which is, what does this look like? I'll just run this test. So it's again the same thing. You see this, it's a linear layer. So we've got this done and we've got this done, right? So that's about it. Okay, so we're done with it. and you can also see the result. So that's you got Q prime, then you also got query, and you've also got raw attention scores that we just printed out when we do the calculation, which is this part. Q times K transpose divided by dk times V. When we do all of that, we get the raw attention scores. And then when we apply the VAST, we get this. Interesting thing, when you apply the softmax, you actually get a really sparse matrix with a lot of zeros and ones. Now, this is expected because we've got really large numbers comparatively. As we go along the training process, you'll see that this will change and you'll be able to see a lot more information. And then you get your final attention scores, which is the same, which is what we see here. Okay, sorry. So we basically call the forward method on the multi-head attention block. And where was that? Yeah, so the final attention scores. Once we have the final attention scores, we go ahead and multiply that with, WO. And that's when we get the actual attention scores, or what we call affinity scores, or whatever you call it, the self-attention scores for all the words in that matrix, for all the tokens, sorry. All right, so that's how it's implemented. Yeah, I've got a whole bunch of things that you can play around with over here, some tests, etc., that I've included to sort of get started in the being able to use the Candle framework. Okay, so I hope this is sort of now making sense. Once we have put this block together, everything else in this diagram sort of should be pretty simple. This is the decoder block now. We've pretty much got everything out. We can do the same. Output embeddings can be similar to input embeddings. Positional encodings have been done. The normalization layer is done. The feed-forward layer is done. The multi-head attention block is done. Now we'll look at the masked multi-head attention in more detail. But the moment all of this is done, you can now put together your decoder layer and your encoder layer, and then have your full model, split out whatever whatever probabilities you want to like. If you want to do language translation, vision transformers, whatever it is, sort of build that out. Okay, so in the next session or in the next stream, we'll sort of tie everything up, at least one layer. That means we'll tie the encoder in, and then we'll also try to look at the remaining pieces in the decoder. And then we'll try and put this entire diagram together once so that we're in a better position. Okay. Yeah. I hope that makes sense. All right. So that's it for this particular stream, I guess. I don't want this to be too